So welcome to part 2 of the calculations using homogeneous equilibria. We're going to go into the more complicated calculations and the ones you're more likely to see in the exam. So we can see here we've got 2 moles of A, we've got A up here, okay, placed in a 10 decimeter container, so we're going to have to calculate concentrations at some point until the equilibrium was established. Again, we've been given this question 310 Kelvin, that's irrelevant because it doesn't apply to it doesn't make any difference to the calculation. So the equilibrium mixture was found to contain 0.75 moles of A. So we know how much we've got of A, we know what we started with of A, but we don't have B. So calculate the value of Kc for this, so you've got to use the Kc equation. So let's put this over to the side and introduce you to our ICE table. So our ICE table stands for initial, change and equilibrium. Now, the initial is just what's in the question. So you can see here we've highlighted 2 moles of A at the start and there's none of B because it's the product. Nothing's been made of it yet, just 2 at the start. At equilibrium, we know there was 0.75. So 0.75 is going to come up here. Now, if there's 0.75, the difference between 0.75 and 2 is 1.25. Okay, so that is your change. From 2 to go down to 0.75, you have to have used up 1.25. So used up 1.25. If you've used up 1.25 of A, the ratio in the equation is 1A to 2B. So if I times that by 2, I'm going to get 2.5. That means I've used up 1.25 of A to make 2.5 of B. That means at equilibrium, there will be 2.5 of B. Okay, so overall, we've now got our equilibrium number of moles. But now we have to convert to concentrations. And we use our equation concentration equals moles over volume, or N, divided by V. Now, if that is the case, what you do with A, 0.75 divided by the 10 decimeters that's in the equation. Oh, sorry, not in the equation, but in the question. And then that gives you your concentration. We can do the same with B, because the total volume is 10 decimeters. And this works with gases, by the way. So if you've got gases and the total volume is given as 10, those gases will fill the entire container. So that means if your container is 10, your total volume is 10. Now, what we then do is we keep those numbers. Let's put them up there and get rid of our ICE table. And then what we can just start doing is put them into our Kc equation. So we know our Kc equation is going to be Kc, and it's going to be equal to our product. Our product is B. It's the concentration of B squared. And that's because it's 2 in the equation. Right? And then we have over the concentration of A. Now, if that is the case, we've got our numbers, we've got our concentration. All we need to do is put our numbers in. So B, we know is 0.25. So this is 0.25. And that is squared. Then we go for A. A is 0.75. Okay, and so that's 0.25 squared divided by 0.75. Okay, you put that into your calculator, and hopefully you're doing it now. And once we put that into our calculator, that will equals. Okay, and that will equal 0.83. So we've got 0.83. So that 0.83, now we've got to think about what are the units of this. So the units of this are going to be equal to moles decimeter minus 3, and that's going to be squared, over moles decimeter minus 3. So that means that cancels and that cancels. Okay, which leaves behind moles decimeter minus 3. So basically, the units to this are just moles decimeter minus 3. And there you have, you're working out when you're given the volume, you're given the number of moles, and you have to use the ICE method, initial change and equilibrium, to find out your overall value of your equilibrium constant. The last question was the most likely one you're going to see in the exam, but here we could have an added complication of being given the masses before we start. We're given a total volume, so we need to turn that into moles, the masses into moles, and then turn it into a concentration. And we're given the equilibrium mixture of 1.15 of the product NO2. So let's do the Kc and give the units. So we've got our ICE table. Now the ICE table is initial, change and equilibrium. So we've got it down here. Okay, and all we're going to do is take the numbers from the question here, so 11.04 of N2O4, and we're going to divide it by its molecular mass. And that's going to give us the initial amount of N2O4, which is 0.12. We're also going to take the amount 1.15 of NO2, which is a product, okay, and we're going to calculate that, dividing again by the molecular mass, this time of NO2. Now, if this is the case, 1.15 divided by 46 is 0.025. Now that is the equilibrium amount, but that is also the change from 0 up to 0.025. So we can put it in the change box here. Then there's a 2-to-1 ratio here. So if I divide this this number by 2, I get 0.02125. And this is the amount that's used up to make the NO2 because of this 1-to-2 ratio. Now we've got the initial amount of N2O4 and we've got what was used up. So if we minus one from the other, okay, we will get a 0.1075 moles, which is 0.12 minus 0.0125. And we now have our equilibrium amounts. What's left over for N2O4 and NO2. Let's put this up here. Now we need to convert those values into concentrations. So you do that using concentration equals moles divided by volume. That's derived from moles equals volume times concentration. Now, if that's the case, we just put them in there. So there's your moles, there's your volume, and your volume is taken from the question here, 4.8 decimeter container. Now, you can do that because it's all gases and gases just fill the container, okay? So if that's the case, we've got the concentration of N2O4, which is 0.1075 divided by 4.8, and NO2 is 0.025 divided by 4.8. And both of these numbers are kept in the calculator. That's why we have the 3 dots. They're just the whole calculator number. Do not shorten them in any way. We're now going to do the equilibrium constant equation. And the equilibrium constant equation is just taking that from the balanced equation and turning it into this. Your products over the reactants, and you go to the power of the balanced equation, which is 2. If that's the case, we just put our numbers in. Again, they're from the calculator. Make sure you're good at doing that. We got our final answer, 1.21 times 10 to the minus 3. And it's moles per decimeter cubed is the units. Just going to finish off by saying why they are the units. So if you look here, we've got moles per decimeter cubed squared because of this, and we've got moles per decimeter cubed at the bottom because of this. The bottom moles per decimeter cubed cancels out the second moles per decimeter cubed squared essentially, and you get the moles per decimeter cubed left behind, which becomes your units for Kc